Here is a range of scenarios in which it makes sense to build a smart contract with our experience. Let's imagine that this is a database. We've already seen that we created our database, which has rules that we can define as symmetrical. Every column is a column. It's as if it was a database on its own. So it's an aggregate of databases. Each column is a database. So the reference to this is a public key. We'll call it A, B, C, D, E. So A, B, C, D, E are 5 databases, which together are encapsulated in a single database. Every row is A, B, C, D, E. There's the same identification in the columns. If it's true that A is a database, the rows of A are the other accounts. If, for example, we were the account, I'm A, B, C, D, E. I'm A. I have the control of this database. And I control your accounts. I control your cells. How do I control them? With a smart contract. The smart contract is an application, an app, a software, which can contain methods, which manipulate data in general, sums, whatever, and in general they can access the host functions that allow us to read and write inside. Just inside here, from A I can't access C. It's another database. I'm completely unable to arrive in it, but I can interact with it. How? Asking C to do this for me. So if C is another application, A can call C and utilize the visible functions so I can gain access to this cell, but in reality it's not A that gains access. The context changes, the CTX changes. The caller becomes A, and the caller says, "Excuse me, what's written inside?" And if C permits, it gives a return. If C doesn't permit it, it doesn't get a return. So the same thing goes for writing. This is the principal concept of a smart contract. It's an application that governs a whole database. At this point, what does govern mean? The association between smart contract and account is indelible. Once I've baptized it, there's no way of changing it. So if I have written rules which allow me to modify and add this data, I've written a contract. So I can say, I will write on the account of B only if B wants it. The only if B wants it can be seen by looking at the CTX caller or the public key or whatever. So from the moment that I have deployed these rules forever, the only way to write on C is to obey these rules. It's not possible that within a year A will change the rules. This is the fundamental guarantee for those that underwrite account rules. At this point, someone could say, I want to make a different version of the database, but that's something else. For example, I add a functionality which may not have been foreseen. So, it's not that everything is written in stone, but what's important? It's that those who live inside must respect those rules. So, at a certain point, the branch will dry up. I've done a second version, so the application no longer goes to the earlier version, but those within the first version will continue their operations, and then I will now say that all the operations will be done on another account. The accounts are free, there's no charge. It's free because it's delegated to mathematics. The account is a public key. There's no, as we said before, method for saying add an account because the accounts are already conceptually within the database. So this matrix is an infinite matrix, but it's never instanced at an infinite level. It is instanced on the basis of what's required. And it's potentially infinite, but in reality it's finite depending on what use is made of it, and not for the account. Because when you instance a transaction, the transaction understands that these 4 cells are involved. It reproduces this table limited to just these 4 cells. So conceptually it's infinite, but in practical terms it's finite. Given this is what happens within the database. If I imagine, let's imagine a series of smart contracts. The first is the classic money. This is my database. As it's money, we did a method that we call mint. Mint invents money from nothing. As the argument, we'll put 2. Comma units. And what does mint do? For example, I don't want that everybody can invent money, so I can make an if context dot caller coincides with ctx dot owner. What does this mean? It means that this is only one slice of the database, but looking from outside, I've got A who has A, B, C, D. CTX docs caller equals CT docs owner means that I'm just looking at A that manages his cell A. In this case, I can say let's do some high-level reasoning. I can see the value of the cell. Amount equals get data of 2. To A dot write 2 comma units. What would it do? Only the owner can add but not overwrite new money to those that have got it. Whoever can call it. If this condition is not met, you can't do the mint. With this simple rule, I created a way of creating money from nothing. But I put in a rule, a simple rule. I can make other conditions. For instance, only who has at least 2,000 coins can make a mint. And this is how the blockchain works. When you create a new currency, it's the rules of who makes the mint, who makes the burn, who makes the transfer, how the transfer works. We've got all this. Already we offer ready-made smart contracts to make money. But who wants to create a new money can invent their own rules, even mad ones. So this is the way of doing mint. Let's see how transfer is done. Maybe for the first time you'll see how the banks create money. Money here's our A, B, C, D, E. We've seen that the mint, the first transaction creates 10 units for B. That's all. Now let's try and do a transfer. Transfer from to units. What rules would you apply to make a transfer? Conceptually, we put if units are less than or equal to the from units. If I leave it like this, anyone who calls this function can take them away. If ctx dot caller, i.e. the one who's calling, equals from, so we've created a money. This is a simple rule to create money. So the complexity is added by the node and other things, but it's no longer a game. On a database, if you create money on SQL, it's easy, but afterwards you're responsible for all that money. You have to keep it, you have to do backup. If somebody says, take all the money away from Luca, if you do it, Luca says, why have you taken my money away? I trusted you and you've taken all my money. Earlier, we did an exercise that's important. The boy who designed this system, I provoked him. I said, try and take all this money. You can't do it. Not because you don't have the will to do it, you don't have the instruments. If you try and do it, the transaction says, or the network says, I will not allow this. So you begin to enter into something where there's no need for the trust of the company. Today, we trust Amazon. You buy a product and you don't worry about it. It'll send it. I give them my credit card. I don't lose sleep worrying about Amazon taking all my money. I trust Amazon, but Amazon's big by now. If I open a small company, maybe somebody in Singapore says, how do I know what you do with my data? You're not Amazon. You're something, you'd say, yes, you're right, I'm not Amazon, but I did this. Just trust what I've written. I can't change it. If you trust it, then you can be happy that we'll respect all the obligations. But it's the network that makes sure we obey the rules. Otherwise, you can go to Amazon. In fact, with this technique, we've created the escrow. I'll explain it like this. We've seen what does putting a smart contract as governance of an account. We could also make it as governance of a wallet. This is account A. This is account F. Let's say in A, they're embedded. The money we talked about earlier. And the transfer method is written slightly differently. The method says like before, but before proceeding, it checks that it's him who's making the money, but also it does an additional check. It checks to see the from has a smart contract. So what does this mean? When Mr. F gets here and he says, move my money from F to B, he checks that F has the money and says, it's not that you've got a smart contract in your F, and it turns out yes. It says, I won't transfer the money. I will evoke your transfer. So I do a call on F with the method of transfer, and I pass the same arguments of the transfer. At this point, the smart contract gets here and it blocks itself. F's smart contract is uploaded and asks, what does your transfer foresee? My transfer foresees other logic. For instance, the context.caller has a mandate, a certificate. A certificate of belonging to a particular company. If he has it, it returns true, otherwise false. What happens? The money behaves normally and gets here and says, hey, this guy's got a smart contract. Hold on, let's wait a moment. Before moving the money with the basic rule, let's see if he has foreseen some rules. Yes, he's got some other rules. I go back, I return false. I won't move the money, even though he has satisfied the rules. This permits us to do what in the majority of programming languages is called extend. I can declare a new class, extend the transfer method, and call up the super. I can add. Why has it been done like this? Because I could have done extend only in the same context, in the same computer, but imagine smart contracts can paradoxically live in other computers. How can I extend to a class in another computer? But with this technique, you extend the logic. It says, hold on a moment, you're the parent class. Let's go and see if the final class has your method. Use that method. This is what worries about relaunching the transfer. And when he launches the transfer again, he does a cdx.call. And at this point, he continues, he becomes the new caller. So he remains F. Nothing has changed within the context. It was before F, now it's F. But it's changed to the additional logic, which paradoxically could be to halve the money. I can do a smart contract where if you say to move 10, I move 5. So who can make a rule like this? Think about it. It can be F on F. So I can't, if you give me 10 euros, give you 20, unless you, in your account, have the same rule. So you wanted to change the rule of the transfer, and as you're a benefactor, for every coin you ask to move, you give 2 to the orphanage. I understand that this is not such a stupid rule. It's called cashback. Every time, for example, I can create a context in which I take money, like crowdfunding. Every time I spend money, I give 10 to you, and 10 to you, 10 to him, 10 to you, 10 to him. And then I finish, that's the end of the story. But I have promised indelibly to the world to give half the money to him every time I spend it. Try and do this with a bank. This is customized money, customized rules that create a new money. These are infinite possibilities, and clearly these possibilities are all contractualized. And they must respect a business model. For example, our group, we've created a cash book system for which every transaction done on e-commerce, you get money back. And it's not Affidaty that guarantees this, it's the system. As long as there are the conditions, you buy it on the e-commerce, you get the money. It can't fail. And you can't change a smart contract. To revise it, you have to move it into another account. In fact, there are techniques of proxy in which, if this is the account A is the money. So once I've done this, I can't revise this. I don't need to be able to change it, because what would it mean if I create the euro and then change the rules? I've created a contract with the euro. But at a certain point, you do your smart contract on the account F, which is an escrow with certain rules. All those who have started to use your smart contract within it have a bug. You've made a bug, so you can't impede them unless there's the collaboration of all. In which case you say, lads, I've made a mistake, retake your money and we'll send it somewhere else because I made a mistake. If they agree, that's okay. If they don't agree, you can't force them because you've underwritten a contract. But what happens? Let's say there are 4. And it's your application that has created the TX, which sends this here. At this point, you create the bag and you put it on G. From this moment, your TX sends to G, and all new users go on G. It's not so impossible to manage, but it's fundamental that those who agree to F can't change without their agreement. Otherwise, you change the base on which they function, and if you don't have their agreement, you can't do it. Let's take the example of an escrow. An escrow works like this. Subject A has to send money to subject B. Subject B promises to give a service to subject A. Who sets off first? B gives the service to A, or A gives the money to B to get the service? You don't know. If the process gets blocked, one or other gets cheated. So we use an escrow process A, escrow B. A sends the money to E, and there's a smart contract which governs this kind of principle. The smart contract is programmed that it can't be managed by anybody. It's self-consistent. So sends the money to E, and A has said, I'm waiting in the arguments, I'm waiting for a service from B, and it specifies what this is. And the smart contract says to A, you can take your money back whenever you want to. The same thing for B. I can say, you do the service, but in a moment I can remove it. If, on the other hand, when I give the service, there are money, the money goes to B, the service goes to A, otherwise they stay parked here. And the same thing with funds. You can write this in 10 minutes, and it permits us to do sale of luxury goods all around the world, in which there's no trust between who sets off first, but there's a guarantee that when the conditions are met, the exchange is made. Otherwise, anybody can step back when they want to.